All right, today we're jumping into a real classic computer science puzzle. It's called the N Queens problem, and it's basically a masterclass in a super powerful algorithmic technique known as backtracking.
So, what's the big idea here? The challenge sounds simple enough, right? Just place a bunch of queens on a chessboard so that none of them can attack any of the others. But as you can probably guess, the bigger the board gets, the more this whole thing just explodes into chaos.
Before we can even think about solving it, we've got to lay down the ground rules. What does it actually mean for two queens to be able to attack each other? Let's get really clear on the constraints.
So, here are the rules of engagements. You know how a queen moves in chess? It can go any number of squares along a row, a column, or a diagonal. Our job is to place all our queens in a way that no two of them share any of those attack lines. Okay, so what's your first instinct on how to solve this? You'd probably go for what we call a brute force method, just trying every single possible combination until something works. For a standard 8x8 board, that sounds painful. Yeah, if you think about it, for each of the 8 rows, you could place a queen in any of the 8 columns. That's 8 choices for the first row, 8 for the second, and so on. That's 8 to the power of 8, which gives us this number, almost 17 million possibilities. Trying to check every single one of those would take forever. There's got to be a smarter way. And of course there is. By applying just one simple logical rule, what we call an explicit constraint, we can slash this problem down to a much more manageable size, like instantly. Here it is. This is the big aha moment. We already know from the rules that you can't have 2 queens in the same row. So why not just decide from the start that we're only going to place 1 queen per row? Queen 1 goes in row 1, queen 2 in row 2, and so on. All of a sudden, the problem isn't about picking from 64 squares anymore. It's just about choosing 1 column for each row. And just like that, the whole problem transformed. And this is just beautiful. It shows you the power of thinking about the constraints first. By making that one decision, our number of possibilities plummets from nearly 17 million all the way down to 8 factorial, which is just over 40,000. We got rid of millions and millions of dead-end possibilities with one single clever rule. Okay, but we're not out of the woods yet. We've taken care of the rows, and since we're only picking 1 column per row, we've handled the columns too. But what about those tricky diagonals? That's the part that's left, and this is where the really smart algorithm has to take over. This brings us right to the heart of the solution. It's an elegant, surprisingly intuitive strategy, and it's called backtracking. The whole idea behind backtracking is actually pretty simple. You try to build your solution one piece at a time. After you make a move, you check, did I break any rules? If the answer is yes, you don't keep going down that broken path. You just undo your last move, you backtrack, and you try the next option. It's exactly like walking through a maze. When you hit a dead end, you don't just stand there pushing on the wall, right? You turn around and you try a different path. Take a look at this diagram. This is basically a map of how the algorithm thinks. It sees the problem as a tree of choices. It starts going down one path, placing queens, but the moment it hits a spot where it's impossible to continue, you can see them here, marked with a B, it just stops. It knows that whole branch of the tree is a failure. So it climbs back up the tree, it backtracks, to the last place it made a choice and tries a different branch. Okay, theory is great, but let's make this real. We're going to walk through a smaller version, the 4 queens problem, to see exactly how this whole backtracking thing works, step by step. All right, let's go. First move. We'll place our first queen in the top left corner. Row 1, column 1. Easy enough. Now we move to row 2. Where can our second queen possibly go?
So for row 2, we can immediately see that column 1 is blocked by the queen above it, and column 2 is blocked by the diagonal. So the first safe spot is column 3. We pop queen 2 right there. Okay, on to row 3. And we've hit a wall, a complete dead end. If you look at row 3, every single square is being attacked by one of the first 2 queens we placed. There are no safe spots at all. This path is a total failure. So what now? Does the program just crash? Nope. It's smart. It recognizes that its last decision, placing queen 2 in column 3, is what led to this dead end. So it knows it's time to backtrack. So it just undoes that last move. It picks queen 2 up from column 3 and says, okay, let's try the next valid spot in this row, and that spot is column 4. From this new board state, the search for queen 3's position starts all over again. And the algorithm just keeps doing this little dance. Place a queen, check for conflicts, hit a dead end, backtrack, try the next spot. It does this over and over until finally, bam, it lands on a valid solution. For the 4 queens problem, one of those solutions is putting the queens in columns 2, 4, 1, and 3.
Now that we've got the intuition down, let's take a quick peek under the hood at the formal algorithm, the pseudocode that actually makes this backtracking magic happen. Now, this might look a little intimidating, but the idea is exactly what we just walked through. On the left, you have a helper function called place. You can think of it like a security guard. Its only job is to check if a square is safe to place a queen on. On the right is the main event, the n-queens function. It goes row by row, and for each column, it asks the place function, hey, is this spot safe? If it gets a yes, it places the queen, and then, and this is the cool part, it calls itself to go solve the very next row. That's the recursion that drives this whole thing. So why on earth do computer science students spend so much time on this one little chess puzzle? I mean, it's a neat trick, but what's the big deal? Well, it turns out this was never really about the chess. It's about the strategy. This slide nails it. Backtracking is a general-purpose problem-solving tool. It's perfect for any situation where you have to build a solution step by step. By checking the rules at every single step, you can chop off huge dead-end branches of the decision tree before you waste any time exploring them. It's all about being efficient. And that really brings us to the most important question. What is all this for? We've seen how backtracking can solve a board game puzzle. But think bigger. Think about planning a delivery route for a truck. At every intersection, you choose a street. If that street leads to a massive traffic jam, you backtrack to the intersection and try a different street. Or think about solving a Sudoku puzzle. You pencil in a number, but if it creates a contradiction 5 moves later, you erase it and backtrack. The exact same elegant logic that places queens on a chessboard is out there, quietly solving some of the world's most complex challenges.